Okay, so I'm Bruce. I'm a PhD student at the University of Pennsylvania, and I work on machine learning for robotics, to basically using machine learning to get robotic systems to do what we want them to do. So I'm sure before we even get started, a lot of you have some sort of experience with robotics, whether it's from some high school robotics team or just news stories that you've seen, movies that you've watched, or anything like this. So could anybody think for a moment and just drop in the chat any modern applications you know of for robotics, just to see what we think before we go into the examples that I had in mind. Siri. So yeah, Siri is kind of like a chatbot. SolidWorks. So this is kind of a tool for this. Yeah. Factories. Yeah. In factories, you have a lot of automated machines building your various things or moving things around. Yep. Any other applications people can think of? No? Oh, robots that do flips. Yeah, sure. All of those calisthenics robots that Boston Dynamics develops, certainly. Yep. These are all great examples. So I'm just going to go through a couple of them that I had in mind that I thought were compelling. So one example is precision agriculture. So there's people that are trying to use drones to deliver things like fertilizer and water to plants to avoid kind of crop dusting by just flying planes over. And this kind of precision makes sure that you're not wasting a lot of resources. And it also makes sure that you can actually kind of preserve more plants and actually succeed but in increasing the output of your crops. Another example is search and rescue. Oftentimes you might have situations where you have like humans that you need to rescue, but you don't want to put additional human lives at risk by sending them into a dangerous, like collapsed building. So you might send like legged robots in to kind of survey and see who's there and even try to help extract them. And then one other example that's maybe exciting for us in daily life is a home assistant. So something that can go around your house, do your chores, clean up after you, and all this type of stuff, just by telling it what to do. So, well, all of these are fairly different platforms and performing very different tasks. They kind of have the common feature of interacting with some type of complex environment. So in particular, the robot in some way acts on the environment that's around it. This action has some impact on the world, which then it can use to complete the tasks it wants to complete. Now, the challenge with just planning out a sequence of actions and applying them to the world is that the world is a very complex environment. So the surroundings that a robot is interacting with are very complex. So just applying actions and planning out which actions to apply is likely to fail because you're not able to predict the consequences of all your actions. So the other essential feature of robots is kind of some sort of observation it takes of their surrounding world, which kind of provides feedback to kind of mitigate all of the uncertainty in this complex environment. So with this picture of how a robot interacts with the world and obtains observations, let's brainstorm for just a minute and think, how might we apply machine learning to an example such as the home assistant? What types of different machine learning algorithm strategies can we apply? Which algorithms do we apply? And what can they do for us? Feel free to drop some answers in the chat. Learning what music you like and when to turn the lights on and off. Sure, right? You could have a home assistant that's, I mean, it's really a robot that's turning on and off lights. Sure. A pathfinding system to navigate around your house. Sure. Recognizing objects in front of the robot. So this is a key one, using kind of computer vision to detect objects. Movie recommendations, okay. Vacuum robots, so they're using machine learning, certainly. Yep. So let me go through a couple of the specific use cases that I thought of that are kind of in use in a lot of robotics research and even deployed robots. So one of them is something like natural language processing. So oftentimes you'll give your commands in a language, and then you want the robot to understand from your commands what it should actually do. So it'll process your language and convert it into tasks that it can understand. There's also making sense of the environment, so kind of detecting objects, determining which objects are where in your environment. And something that's somewhat unique to robotics, or at least to decision-making systems, is kind of predicting how the action will impact the world. So if you uh, move your joints in some direction, what impact will that have on the environment around you? So oftentimes this will also be done using data. Okay, so with kind of this diverse set of uses for machine learning in robotics, what are some of the potential dangers that arise from applying machine learning for robotics? They take over selling data. Okay. Is there anything specific to something like robots that you didn't see maybe in some of the other machine learning algorithms that we had that we didn't have with just something like natural language processing? So there's a few good answers here. So it could learn dangerous habits. Um, it could take people's job. This is certainly an ethical concern of it, but some of the errors that it can make, it has physical parts that could cause danger. This is a really essential one, right? So a lot of algorithms that we make, they might output some decision that's then evaluated by a human, but a robot is interacting with the environment kind of without human intervention. So the physical parts that it has could really be a danger. So I think you had a lot of good answers here in the chat. So I just want to emphasize a couple of them and maybe reduce a couple of them down to their essential point. Is danger one is that you're computing actions without human intervention. So in contrast to something like a chatbot where you're supplying some input, evaluating its response, and kind of you can determine whether you should trust it. In a robot, when you have a machine learning algorithm in sort of this control loop, it's got to trust whatever the output of the algorithm is. It doesn't really have a choice of saying, I don't trust this, or like, let me run this by a human, because it needs to really operate autonomously. And the second aspect that is kind of a danger is this feedback loop. So because the actions that the robot takes impacts the environment, which are then observed by the robot, it means that initial small errors caused by the robot, so incorrect actions, might lead it to some part of its environment where it hasn't seen a lot of data before. Because of that, it might not correctly process the observation that it sees, and it may kind of cause some sort of compounding error. So the failures that it makes will kind of compound and might lead to catastrophic failure eventually. So the kind of core of my research is determining how can we actually trust learning robots. So when we apply learning in robotic systems, how do we actually ensure that we can trust it? And I think there's really two complementary approaches. The first one is extensive verification. You really won't trust a system until you've seen a lot of evidence that it will work well in the real world. The challenge with extensive verification is before you trust the system in the first place, it's really hard to actually deploy it in the world in order to gather that evidence. A partial solution to this is to use simulations of the world. So in a simulation, you can deploy your algorithms, and a failure really won't hurt anybody because there's no physical robot here that's actually performing all these actions. So a simulation is a good way to test your algorithms and kind of verify that they will work in the real world. The issue with using a simulation is, even if it works well in simulation, if anything that you didn't model correctly about the real world might cause your algorithm to fail when deployed in the real world. So a complementary approach to this extensive verification is trying to design algorithms that are just safe by construction. So the way that this works is you assume some sort of adversarial model of how the world interacts with the robot. So the world is in some way acting to make the robot fail in this model of how your environment works. And you try to design algorithms that work even in the worst case settings. So as long as you've modeled your world worse in some way than the true world is, you're guaranteed that your algorithm will actually work well in the world. So your robot will be safe in the real world as long as you've designed a sufficiently adversarial model for the world. So most of my research is really actually in the second area. So it's about how to actually model a world as an adversary so that when you design your robotic algorithms, it will actually be safe when you deploy it in the real world. So with this just like high level overview of robotics, I'll just end here because I think I'm nearly out of time. So I'll just take any general questions you might have about deploying machine learning for robotics.